After we get to the scaling, it's actually far less intuitive, so you probably want to listen up to this part. We are subdividing the curve, and then we're going to find all the points and test them against one another, and then we'll multiply that numerical relationship and feed it into the factor. Making sense conceptually? All right, so here's what it looks like. We go up to the curve tab, and we go to division, and we click on divide curve. That part's pretty intuitive. Curve, division. It has a couple of properties inherent to that node. So we've got the curve that we plug in, and we have to reference that one in using params. It has a count, which has a default value of 10. Usually, especially when I have a compound curve like this, I want to bump that up to like 40 or 50 or something like that. A lot of points. And K, split segments at kinks. I guess that's when you have an actual angular division to your curve. That's my guess. I've never used it. So anyway, I'm just trying to explain it to you. So the curve itself gets referenced by going up to curve under params. And then you right click and go to set one curve, click on the curve, and plug it into C. And take a look at what it's doing. Along the length of the curve, it's creating a series of points. And that's all well and good, but my points are very irregular right now. If I want a very smooth, fade to the pattern, then I want to bump up the number of points. So that's what I'm going to do. I'll say 0 less than 50. I'll probably wind up putting it somewhere in the middle, like 25-ish. That should work out quite well, I think.
My points disappeared.
Did you?
Oh.
Yeah.
Oh, yeah. That'll do it. Make sure your count is more than 0. So then here's where it gets a little dicey. Okay, so I'm introducing a different concept to you now. I'm introducing the idea of domain as a minimum and maximum value, right? So it becomes a range, not a proportional percentage. Does that make sense? Well, I mean, a range kind of is a proportional percentage, but it's not something off of a static number if the number changes, right? So we'll look at the data and then we'll start moving things around and you'll understand what I mean. But to make the connection here, we actually have to test the points against the points of the squares against the points of the curve. Okay, and that's under vector, point, and forgive me for getting confused about this, but I do every time the difference between closest point and closest points. It's counterintuitive, but I'm pretty sure that you want closest point when you're testing against multiple points, and you want closest points when you're testing against a singular point. I know, it's so silly. Or at least that's the way I have it set up currently. But if you click on closest points, plural, that would be the one that we want for this particular instance. Yeah.
Wait a minute.
Did I click on singular? Yeah, that's what I mean. Closest point, singular. Yeah. I'm making it worse, guys. Sorry. All right. So for this, it asks you for two things: the point to search from and the points to search, which is saying what's being tested for and what's being tested against. So the points to search from are all of the points of your grid, which for us, I wonder which one I would actually want to use to make it more accurate. You probably could use the centroid, but you definitely can use the original grid points. Actually, it's probably better to use the centroid. Let's use that. because the centroid is more accurate. And then the points to search would be the cloud of points on the output of your divide function. So don't worry so much about the tangent or this is your numerical, what is that? I don't know what that is precisely. Parameter values at division points. I would think that this would have an X, Y, and Z, but maybe not. It doesn't really matter all that much because I have actually never had to use that. Or, oh, I know what this is. This is going to be the length or the distance of that point along the line. Right, so similar to the circumference of a circle, right? You measure the distance along the, you get it. Anyway. All right, so here we go. We're using closest points. And take a look at what it's doing. Okay, so let me slide this aside. So it's already collecting only particular data. And let's look at what data it's collecting. So I will say that the way that this works is that it's finding the closest point, singular, in a point collection. So that means that it's going to test all of your cloud of points for its one closest point. You understand what that means?
No.
So the points that you're testing are all of the grid centroids. Right. So any of these points are not closer to this point than they are to this. So that's why those get omitted, because they're not the closest point to anything. Make sense? So that's just the premise of that and how that works. But let's push forward a little bit. So the information we get, we have, again, we have our points that we can use. The index, which I probably imagine is setting it up in groups. So if we hover over this, there are probably 11. No, there's more than 11. What's it testing? Oh, the index of closest point. I'll have to look into that one for you guys. But I've never had to actually use that for anything. So this is the big one, okay, the distance. The distance is giving you the numerical index of how far it is from its closest point, right? So those are the two that we need. Well, we don't really need that even. Well, do we? No, we don't. So from that, we're setting up a domain. And our domain is going to say, what is our smallest distance? What is our largest distance? And then we tell it to scale by a certain factor that we say is our new smallest and largest value. Okay, so I'll leave scale kind of off to the right here. Remember, closest point came from vector, vector. Or was it vector point? Vector point. All right, so we've got vector point. What we are doing here, we go under math and we look under domain, and we need two of these. We need bounds, which creates a numeric domain which encompasses a list of numbers, right? So it's going to read a list of numbers and it'll give you the minimum maximum. So I plug that in. The numbers as a list is essentially this distance, right? That's what we're testing against. And what it gives you here, it says one locally defined value from 1.5-ish to 92.5-ish. Understanding a little bit now? That's a math domain. And then the next one is remap. So remap is going to function just basically overriding this output value of 1.5 to 92.5, and we're just going to tell it, take all those numbers and scrunch their proportional relationships down to these new numbers that I just gave you. Okay? So for us, we are overriding that value. So we're going to take our original distance here, and we're going to plug in our test values. So that was the original value. Then we plug in our test values. right? So that's your source domain. And then the target domain. So the target domain is important because you will tell it how big you want it to be, but it has an inherent property as well. So we've got 0 to 1. So let's take a look at, we're going to override this into something else so that you know what it's actually doing. So let's go into, well, let me set that up for you. Maths domain. All right. We go into domain and let's look at constructing a domain. So when it's asking you for a target, it's asking you to construct a domain. See how this is speaking the same language, 0 to 1? That's its default value. That's because at the A input, it's reading a 0, and at the B input, it's reading a 1. So I'll start off with, well, technically you can't have a 0 for a scale factor. So we're going to do 0.01 to 2. Copy that down and plug it into B, but slide it up to 2. This is under math domain, and it's construct domain. So again, looking back, this is where we are. The connection point right now is still the closest point, and we're working off of the distance of those closest points. And we're going to start plugging this back up into the scale factor. Okay, so our domain here, if you look at the output now, it says 0.01 to 2. So when we plug that in, our remapped values, if I open up a panel on it, let me open up 2 panels actually. So our original distances compared to our remapped distances. So remember when, I don't see it up there, but when we were reading the original values, 92.5-ish was our maximum. This is 92.5 here, right? Number 11, or index number 11. So index number 11 over here was remapped to a 2.
What did you connect the panels to?
I connected them to the original distance value, right there. I connected one to that, and then my remapped output is what I'm reading in the second panel.
Oh, okay.
Panel is under params, input, and it's this little yellow one called panel. I know, shocking, right, Gabby? So,
oh, we don't need it. Just we don't need it. Delete it.
yeah, no, you don't need the panels. I was just putting that up there so you could see the information and how it was being modified. Okay, so this is essentially the last step. However, we're probably going to want to add some kind of factor that we can modify, but let's just plug it in to see what it looks like for now. So when I plug the remap values in, this is what I get.
Whoa, whoa, whoa.
All I did was plug in R to the F.
And that made it all crazy?
Well, yeah, because it's multiplying it by all those different numbers.
How does it know where to do it from?
Because, so that's actually a very good question. How does it know where to do it from? Like which ones to scale? So if your list of data is at a different length, then it's not going to read each one tied. It basically reads them as a singular list from 1 to 100, and then it pairs it up and it'll tie it back to the next list, which is 1 to 100. So when we have, if you're looking at the distances, we have 121 distances that we're measuring. Similarly, we have 121 center points, and we also have, back at geometry, 121 rectangles that we're trying to scale. So their index values, as long as the list is flattened, is going to give you that value.
Now, how does it know how big to make it and whatnot?
So that's what we just constructed.
Okay.
Yeah. So yeah, that's so good for asking me to do a recap. Essentially, what we've done conceptually is we've taken our original rectangles and we've measured the distance of their center points to the points that we created along the curve. Then we modified the distance. We modified the distance of the closest point and fed it back in to scale that point by that factor. So we created the distance as a multiplier for its size.
That's pretty cool.
Is that clear?
Yeah.
Cool. All right. So that about wraps this one up. Sorry, there is actually one more. I was saying that you probably want to look at modifying this a little bit more, and that's because, well, when I plugged it in, it came out like this really kind of crazy pattern. And that's because my domain, obviously, was exaggerated. My domain, I went from 0.01 to 2. And I know that my rectangles were sized exactly to the grid that I really wanted as my maximum. So my domain end should actually be 1. So I don't want them to scale above their original size. I only want them to scale up to their original size. And that's how you get something a little bit cleaner like this.
So the boxes are also like whatever's closest to the line is fading away.
Yep. So thank you for that too, because I almost forgot that once you move this curve, all of the information will change too. I can move this curve to the bottom left side, and then the top right side becomes full scale.
Can you also manipulate the amount of points and how it changes too?
Yeah. So I can put it in the middle like this, or rotate it.
That's all right.
Okay.
That's so cool.
It is cool.
That's really fantastic.
Yeah, it is. All right, so we've got a couple more to do on these. So let's. I'm going to stop this video here, and we're going to move forward a little bit to a couple more, slightly more complex ideas.